Okay, let's do one quick example. Oh, does anybody need to see my wall of algebra that should appear? No? From the people I can see, you've kind of got it. Okay, this is not zoomed in enough, I understand. If you need me to go back, let me know. Come on. Zoom, zoom, zoom. Okay. Example number 5. Let's just do these are like our carts, souped up. We have 1,000 kilograms going east at 20 meters per second, and it catches up to a more massive one, also going east, but slower, just like I did with the carts. This one's at plus 10 meters per second. Okay, and so here's object 1, here's object 2. And they have an elastic head-on collision. It's more like front to back. Sure. Oh dear. That's a typo. Let's not do milligrams. It does indeed say milligrams. I'm not going to mess with that. Oh no. Maybe this is old Mr. Watson's notes. Maybe he wanted to. So what happens is if one is super small mass, then it just fires away, and the big one hardly changes its mass at all. But we could look at equations. No, no, no. That's a chemistry problem. That's why you don't feel the air molecules pelting you all the time, because compared to air molecules, you have almost infinite mass, and so they just reflect off of you. Okay, that's silly. We know that. We'll examine that more later if we have time. Okay, so let's just write down our formula like we're desperate physics students on a physics test. I have V1 minus V2 initial, the difference in velocities, and then I have to have a minus sign to make the math work out, and then I do V1 final minus V2 final. They're going to have a same magnitude relative velocity, but the minus sign is flipped. Okay, so 1 is plus 20 minus positive 10. Those are the initial ones. So then I have a total, whoa, that looks weird. I have plus 10 meters per second has to equal minus V1 final minus V2 final. Okay. So I reduce that to 10. I still have two unknowns in that equation, but I also should have one other really easy equation. Which one should I use? Yeah, momentum is conserved. In the universe, it literally has to be conserved. I should scan quickly for an outside force of some kind in this problem, but it's the simplest problem. Okay, so I should also be able to do m1 v1 initial plus m2 v2 initial. The total momentum has to be conserved. M1 v1 final plus m2 v2 final. If it's hard to work with these, write them down on the, even better, I'll give you the test review today, but on the homework, write down the equation that you're using, even in empty variables at first. Okay, that will help you become familiar with it and use it more deftly. Okay, well I know V1 final, and I know M1. Oh, so that's just 20 thousandths newtons plus 20k n dot s. And I know the other one. It's another 20k. Oh. Because it's moving forward 10, and it's got a mass of 2,000 kilograms. Okay. So that equals 2,000. Oh, no, it's 1,000. 1,000 for M1. V1 final plus 2,000. Hey, I could divide everything by 1,000. Make my life a little easier. Oh, look. And what if so I could simplify that equation if I feel like it. If I distribute that negative 1 here, this negative, this equation could really say V2 final equals V1 final added to the other side plus 10. So actually, it's just begging me to substitute wherever I have V2 to plug in V1 plus 10 instead. Okay? So what would you, I'll leave it up to you. You have 40,000 newtons on this left side. Would you divide everything by 1,000? And then do that kind of stuff? Let's see, that's kind of what I would do. Compute real fast for a minute. What do you think? What's V1 final and V2 final? They don't just trade velocities. That's the point of this example. It's not 10 and 20 again. But it's a difference of 10. They better be 10 apart. Because before they were like collapsing at 10 meters per second together. Afterwards they're going to be moving apart at 10 meters per second. Okay. Did you compute? Did you calculate? Oh, don't wait for me. This is your chance. Okay. Did you get plus 6.67 for V1? It comes up real fast. It's the less massive object. It smashes into the other one, but it doesn't bounce off. The other guy's already moving. Rounded to 3 sig figs. Okay, so I would take my own advice and divide everything by 1,000. And you get 40, if it's 1,000 kilograms, you get 40 meters per second on the left side. And that equals V1 final plus twice what's in parentheses there. 2 V1 final plus 20. So you get 20 over 3, or 6.67. And then you add 10 to get V2. So V2 races away. Okay, but 10 meters per second faster. In an elastic collision only, not for an inelastic one, but for elastic only, that will always be true. Because math. Because in order to hold conservation of momentum and conservation of kinetic energy true at the same time, that has to happen. And actually, ignoring a little bit of friction, we see that it does. Any questions? Cool. All right then. And I'll turn you loose.